All right, welcome back. As we get near the end of the course here, the next topic we want to work with are some hydraulic principles and how those apply to brake systems. Let's get started. Okay, I want you to think for a minute about this picture right here. You've maybe seen examples of this before where somebody will lie on a bed of nails or a balloon can be pushed against a bed of nails like that and it won't break. But let me ask you this. What if we did that same experiment, but instead of a bed of nails, we take that balloon and we put it on a bed with one nail on it? Now we go and push down on it. You can bet that that thing is going to pop. So what's the difference between pushing it down on many nails and pushing it down on one nail? What I want you to be able to distinguish in this unit is the difference between a force and a pressure. When this person puts their hand down on the balloon, they're applying a force. But that would be true up here too. If somebody puts a force down on the top of this balloon, the force could be the same. The force isn't what breaks the balloon. As you're probably thinking, that force on the balloon gets spread out when there's a lot of nails. So all those nails are pushing simultaneously on the balloon, and that decreases the pressure. Even though it looks really dramatic, because there's so many nails, there's not that much pressure on the balloon. Whereas here, where there's only one nail, that would create a spot where there's a real high pressure, and that's going to break through the balloon. So let's explore that a little bit more. Okay, fundamentally, this is the relationship that we're going to build on today. The amount of force that we have applied to an object, and force always get measured in pounds. Now, in the metric system, we could measure that force in newtons, but we're only going to work in the imperial system. And so LBS, the abbreviation for pounds, will always be our unit of force. So when you stand on a bathroom scale, you're exerting a force on that scale, and that's what the scale reports. Pressure is a measure of how spread out the force is. You know, you're familiar with pressure because we measure pressure in pounds per square inch, or we often see that as PSI. When you check your tire pressure, you're getting the amount of force spread out over some area. You might hear somebody say that a tire has 35 pounds of pressure. That's really not correct. It's pounds per square inch, or PSI. And area is the measurement of the area that the force is applied over. And area is always going to be measured in square inches, which will typically represent as inches squared. So let's do a few examples here. Let's suppose that there's a 120-pound woman who's standing on one heel, and I've got a pretty high heel shown here, but she's standing on one heel, and she puts all 120 pounds right on that one heel. And the question is, how much pressure is created underneath her heel? Well, we're going to use this wheel. This should go on your conversion sheet, like many of the other formulas we've had. And this is just like the percentage wheel or the torque wheel that we've worked at. If the question is how much pressure is created, we're looking for P. And so the wheel says that to find pressure, we should take the force that's applied and divide it by the area that it's spread out over. Now, we have a 120-pound woman. That is our force. So the force that's being applied downward is 120 pounds. Now for area, we're assuming that only her heel is touching the ground and that the toe is off the ground, and so we need to find out what that area is. A 1/4 inch square, that's not an area. We need to calculate the area. So picture this for a minute. The square underneath that heel, if we could look underneath and see it, would be a square. That heel is roughly square, and each side is 0.25 inches. And therefore, to find the area of that from our geometry section that we just finished is 0.25 inches times 0.25 inches. If you multiply those together, you get 0.0625, and those are now square inches. That is the area underneath her heel. And so that 120 pounds is being concentrated. It's not being spread out at all. It's being concentrated over 0.0625 square inches. So divide that. Use your calculator. Work this with me here. 120 divided by 0.0625 turns out to be 1,920. But 1,920 what? Those are 1,920 pounds per square inch. Or you could say 1,920 psi. And that takes care of it. So that's the kind of pressure. That's a very, very high pressure, but it makes sense. Think about all the force that she's concentrating over that small area. That's enough to break the heel or crush a lot of things that it might be on top of. The key here is we were asked how much pressure. Our wheel tells us that pressure is force divided by area. We were told the force she's applying. We calculated the area, and that allowed us to find our pressure. Let's do some more examples. Okay, in case you've never seen one of these before, this is a funny little contraption. It's a heavy-duty balloon that attaches to your exhaust. I'm going to play a little video here.
But nothing like an ARB X-Jack. What's that? Did you get the back wheel off too? Keep going a little bit more. Is it hard to hold? Okay, that's good. Check it out, guys. This is really cool. That's not even the full lifting capacity of the ARB X-Jack. And I've got the transmission in 4-wheel, so you can see both of these side tires are spinning freely.
Now, if you wanted to see more about that, you can go to YouTube and search for exhaust jack, and you'll find all kinds of products out there. But it's a real product, and as you saw, it really works. So here's the question. The diameter of this jack, this orange bag that we have, is 16 inches. And the question is, if we can get about 5 psi of pressure out of the exhaust system, what is the lifting capacity based on that pressure? So here's what we've got. Inside the bag, we don't have a force, but we have 5 psi in exhaust pressure pushing out in every direction, and that's limited a lot by how good your exhaust system is if you don't have any exhaust leaks, but that's pushing out in every direction. But the only direction that matters is the upward direction, because that's where the lifting occurs. So what is the lifting capacity? That is to say, what is our force? From our wheel, we know that force is pressure times area. And so if we want to find our force, we're going to take our pressure times the area. So we already know the pressure. The pressure is 5 psi. Now our area, well, we got to find out what the area of the top of this bag is. The area is a circle. I'm drawing it in perspective so it looks a little flat, whose radius then must be 8 inches. And so our area is going to be pi times 8 inches squared. Note that we don't need the volume. We don't care what the volume of this bag is. It doesn't even matter how tall it is. All that matters is the top of the bag. And if we multiply it out, we get an area of about 201.1 square inches. So each one of those square inches on the top of the bag, if you want to picture it, each one of those square inches, 1 inch by 1 inch, has got 5 psi pushing at it. And there's a lot of them. There's a lot of 1 inch squares up there. So 5 psi times 201.1 square inches, that is our force, that is our pressure times our area. And that gives us about 1,005.5, or about 1,006 pounds. So about a half a ton of lifting based on that pressure. If we want more lifting force, well, we either need a bigger bag so we have a larger area, or we need more pressure. We need to rev the engine or seal up the exhaust a little better. Okay, so let's look at that problem from a different angle here. Let's suppose again that the diameter of that jack is 16 inches and that the weight of the car is 3,100 pounds. If we want to lift just the front quarter of the car off the ground, then how much pressure do we need? Well, once again, our wheel says if we're looking for pressure, we're going to take our force that we need to create and divide it by the area. So to find our pressure, how much force do we need? We don't have to lift all 3,100 pounds. We only need to lift a quarter of the car, that is to say one wheel. So 3,100 times 1/4 or times 0.25, that turns out to be 775 pounds to lift just 1/4 of the car. So we need to come up with 775 pounds. The bag is the same. The diameter is still 16 inches. We don't need to redo that math. We already showed that the area is 201.1. My board is not picking up my decimal places very well. 201.1 square inches. And we end up with about 3.9 psi. That's how much pressure we'll need to come up with in order to lift it. If we can't make that much pressure, we're not going to get the wheel off the ground. Okay, for those of you who have gone to Harbor Freight, I know I do, and I'm sure that some of you have been there, they sell these little air compressors for about 10 or 15 bucks, and they're rated, you can see it on here, they are rated for 250 psi. That's an awful lot of pressure to get out of a little plastic air compressor. So how can that possibly be? Well, the trick is it's all about the piston area. The question here, the tiny little piston that's inside of here, it is not very big, but there's a real little piston in here that's being driven by the electric motor that's down in here. What piston area will yield this high pressure? Well, again, let's go to our wheel. This time, though, we're looking for what piston area. We're trying to find our area. The wheel says that if we want to find area, we should put force over our pressure. Now this one's pretty straightforward because we know how much force we apply. The piston gets pushed with 10 pounds of force, and so that's going to be 10 pounds, and we're going to divide that by a pressure of 250 psi. And if you divide that, you get 0.04. Now what are your units on that? Well, our area is always in square inches for our calculation, 0.04 square inches. And that's very, very small. A square inch is just a little inch by an inch. 0.04 square inches, that's smaller than the woman's high heel that we saw earlier. That's about the size of the tip of the eraser on your pencil. It is really small. And that's how that tiny little 12-volt motor in here is able to create such high pressure. So I want to bring this short topic to a close here, but let's talk about how this works within your brake system. Within your brake system, think about what happens. When you push on the brake pedal, you push on your brake pedal and that lever squeezes in on the brake fluid inside your master cylinder. There's a real small piston inside your master cylinder that acts like the high heel from our first example, and it squeezes in on this brake fluid, and what it does is it creates high pressure. It creates high pressure due to that high heel effect because we take all the force of your leg and concentrate it over such a small piston. Now that high pressure then gets sent out to each of the actuating mechanisms in your wheels, whether it be a brake shoe or a brake caliper, and then each caliper allows that brake fluid, kind of like the exhaust jack, to push out on the piston which clamps against your brake pad. And so your exhaust jack then takes that high pressure and turns it into a very large force, and that's how your vehicle is able to stop. So let's work through that part by part. The first thing we got to recognize is a formula that deals with your brake pedal. Okay, your brake pedal actually does a lot of the work in your braking system. So here's a formula you need to have. Your brake pedal mechanical advantage. The mechanical advantage of your brake pedal is a lot like your rocker arm ratio, which we already worked with. So the difference is the fulcrum is up here on a brake pedal. The pivot point is at the top. So that's your fulcrum. This point right here is our output point to master cylinder. And of course down here at the bottom, so to get the mechanical advantage, we have to divide the distance from the pedal all the way to the fulcrum. And we divide that by this distance right here, which is the fulcrum to the master cylinder. The math is slightly different, but the idea is exactly the same as a rocker arm ratio like we saw a couple of lessons ago. So let's crunch some numbers here. Suppose I give you these dimensions. Let's suppose the distance from our master cylinder up to our fulcrum is 2.5 inches. And suppose the distance from the pedal up to the master cylinder is 10.5 inches. Now be careful here. I'm giving you the distance up to the master cylinder pivot point. That's 10.5 inches. When we go to get our mechanical advantage for this brake pedal, the pedal to the fulcrum, every picture is going to be different that you're going to see, but the pedal all the way up to the fulcrum would be 10.5 plus 2.5. That would be 13 inches if we add these two dimensions together. So our pedal all the way up to the fulcrum is 13 inches. And we're going to divide that by the fulcrum to the master cylinder. That's going to be 2.5 inches. The units cancel as it always does, just like in rocker ratios. And we end up with 5.2. And so since that's a ratio, we would say the mechanical advantage of our brake pedal is 5.2 to 1. Now we can go a little bit further than that. I'm going to note that our brake pedal here is a 5.2 to 1 brake pedal and build one more idea. Here's why that number is important. Suppose you're driving your car and a deer jumps out in front of you, and you, with your fancy shoes here, go and push on that brake pedal with 40 pounds of force. The brake pedal acts like a lever, just like your rocker ratio, and the brake pedal mechanical advantage tells you how much this gets multiplied. So the amount of force that actually goes in on your piston inside the master cylinder, that is to say the force on your brake fluid, is much higher than 40 pounds thanks to your brake pedal. That's going to be 40 pounds times your brake pedal ratio of 5.2. And if you multiply that out, you get 208 pounds of force. Now, that's not pressure. We would need to know how big this piston is to figure out our pressure, and we'll do that in the next example. But the key is, even though you're only putting in 40 pounds, because of the leverage that you get out of your brake pedal, it becomes 208 pounds up here inside your master cylinder. So let's go a little bit further with that. The master cylinder below has a piston diameter. The master cylinder shown here has a piston diameter of 0.750 inches. We're going to put 80 pounds of force on the brake pedal here, and we want to know how much pressure there is in the braking system. Okay, we're going to start out the same way. Figure out the mechanical advantage of our brake pedal. The mechanical advantage, or MA we'll call it, is the distance from the pedal all the way up to the fulcrum, which in this case we'd have to add those two together. That's going to be 9.75, because the 8 inches is only up to here in this picture. And we're going to divide that by the distance from the master cylinder to the fulcrum. That's 1.75. Units cancel, and we get about 5.6 to 1. There's no rounding rule here, but 1 decimal is typically good enough, so we get a 5.6 to 1 mechanical advantage. Now here's the thing. How much force is there actually pushing in on our brake fluid here? Well, the amount of force isn't 80 pounds. The amount of force that we have right here is going to be the 80 pounds that you apply times the mechanical advantage of our brake pedal, or about 5.6. And so that turns out to be about 448 pounds of force on our brake fluid. That's a lot more that you're providing with your leg. And although we're not going to do the math on that here, most modern vehicles have got a brake booster that helps that out even more. But we're going to ignore that in the work that we're doing right now. Now we can answer the question. The question is, how much pressure is there in the braking system? Well, here again, if we want to find pressure, we're going to take the force that's applied and divide it by the area that it's concentrated on. So we now know that our force is not 80, it's 448 pounds divided by the area. Well, shucks, what is our area? We're told that the diameter is 0.75. That's not the area. The area of that piston, that's a little circle. We know it is because we're given a diameter. So area is equal to pi times the radius squared. Now if our diameter is 0.75, we have to divide that by 2, and our radius is 0.375 inches squared. And that means the area of that master cylinder is 0.44 square inches. That is our area that our 448 pounds is concentrated on. And if you divide that, you get about 1,018 psi. So just you pushing on the brake pedal, along with the help from the small piston in your master cylinder and the brake pedal itself, are creating over 1,000 psi in the brake system. 1,018 psi. That's a lot of pressure. And that is going to get sent out to each wheel to do the braking. So let's see what happens at one of the wheels. That 1,018 psi that we just calculated is going to go into a brake caliper, and it's going to push out on the piston of the brake caliper, and that's going to do our braking. Now, we have a 1.750 inch piston. Whenever we talk about a piston, we're always giving the diameter. So 1.750 inches is the diameter of that piston. We need to calculate the area. So since it's obviously a circle, our area will be pi r squared. Our radius must be 1.750 divided by 2, and so our radius is 0.875. And so our area is going to be pi times 0.875 squared, and that means our area turns out to be 2.41 square inches. That is the area of this piston, and that's the area that that brake fluid can push against. So the question of how much clamping force, well, here again, force is pressure times area, and we now know both. And so our force will be found by taking our pressure of 1,018 psi, as we saw in the last slide, times an area of 2.41 square inches. Means that the clamping force on that piston is about 2,453 pounds. So there's over a ton, almost 2,500 pounds of clamping force on the brake pad, and that's what'll slow your car down. So I want to review what happens here. You start out with a mechanical force, a physical force that pushes on the brake pedal. Your brake pedal increases that. Your master cylinder takes that force, that hard mechanical force, contains it, applies it to a fluid, and it turns it into a pressure. That pressure is in the form of brake fluid, and that goes out through your brake lines. Then once it gets to each wheel, the calipers, or wheel cylinders as the case may be, take that pressure, make it push against a piston, and turn it back into a hard mechanical force. Okay, I've got one practice problem I'd like you to work here before we close this lesson. So I'm giving you a simple brake system with some dimensions here. The distance from the fulcrum down to the master cylinder is 2 inches, and from the master cylinder down to the pedal is another 7 inches. I want you to use those dimensions to figure out your mechanical advantage. I'm giving you a master cylinder with a piston having a diameter of 0.65 inches right there, pushing on our brake fluid. And then that brake fluid goes out to push on a caliper whose piston diameter is 2 inches right here. And we're taking 90 pounds and putting it on the brake pedal when we hit the brakes in a hurry. Go ahead and work that problem from start to finish and unpause to see the solution. Okay, here we go. I'm going to start at the top. The mechanical advantage of our brake pedal is a grand total of, from the pedal up to the fulcrum, that's 9 inches. So we're going to divide 9 inches from the pedal to our fulcrum, divided by, from the fulcrum to the master cylinder, that's only 2 inches. So 9 inches divided by 2 inches, units cancel, that's going to be a 4.5 to 1 mechanical advantage. That's our first step. Now our second step is to multiply that by the force that we apply. We're putting 90 pounds of force on the brake pedal, and so our force on the brake fluid is 90 pounds times 4.5. That turns out to be 405 pounds of force right here pushing in on the brake fluid. That's step 2. Now, the master cylinder turns that force into a pressure. So the system pressure is going to be force divided by area. That's 405 pounds. Divided by our area. The piston diameter is 0.65. And since the diameter is 0.65, we can divide that by 2 and note that our radius is 0.325. And so our master cylinder piston is 0.33 square inches. So our 405 pounds is going to get concentrated over 0.33 square inches. That means our brake system pressure is about 1,227 psi. So that 1,227 psi is in here in our brake fluid, and that fluid gets squeezed down through our brake lines, which hopefully don't burst, and in behind that piston. It's going to push that piston out. So now the last thing we need to do is figure out how much force our piston applies on the wheel caliper. So our caliper piston area is going to be pi times, it has a diameter of 2 inches, our radius is obviously 1, and pi times 1 squared is 3.14 square inches. And so our final step, since we know the system pressure, our final step is to calculate the clamping force. Force is going to be pressure times area. That's 1,227 psi times 3.14 square inches. And we get 3,853 pounds of clamping force. So we're talking about nearly 2 tons of clamping force being squeezed on our brake pads here to bring the vehicle to a stop. So here again, we started with the mechanical advantage, and then we multiplied that by the force that we apply, and that gave us the amount of force on the brake fluid. Then we take that force, divide it by the area of the master cylinder piston, and that gives us our system pressure. That's what causes rusty brake lines to pop right here. Once we know that system pressure, it travels out to each of the wheels, and the caliper is designed to turn that pressure times its piston area back into a force, and that does the job. All those things are based on our initial relationship that ties force, pressure, and area together. Make sure that and all the other formulas from this section are on your conversion sheet, and that's what we need to know for this topic. So watch for your homework on Blackboard, and we'll see you in the next lesson.